Assalamualaikum, we are from group 9. Now we want to present a thermodynamic project. So our selected thermal power plant is Pengerang Cogeneration Plant, Pengerang, Johor, Malaysia. So this is our team member, Ahmad Shafi'i bin Muhammad Adnan, it's me, RM24207, Nazmi Wafi bin Azrul Ezal, RM24242, Muhammad Nur Hafiz bin Muhammad Shahar, RM24270, and last Muhammad Haji Kamal bin Zamsul Kamal, RM24996. So now I want to present a background of our selected thermal power plant. So the Pengerang Cogeneration Power Plant, aka PCP, is a large-scale natural gas fire power. It is located within the Pengerang Integrated Complex, aka PIC, at Johor, Malaysia. It was operated by Pengerang Power SDN Berhad, a wholly owned subsidiary of Petronas. So the technology used, it uses cogeneration technology, which is simultaneously produces electricity and industrial steam from natural gas, significantly improving energy efficiency compared to conventional power plants. And for the achievement of this company, in 2024, the plant won the Sustainable Plant of the Year award at the Asian Downstream Summit Awards, recognizing its digital-driven improvements in efficiency and reduction in fuel consumption and carbon emissions. Yes, now I will explain how the cogeneration process flow. So it will start from the natural gas is supplied from the LNG terminal to the plant, and the gas is burned in the gas turbine to generate the mechanical energy. The mechanical energy is the energy that drives the generator, for example, to produce the gross electricity. And the hot exhaust gases, which is 500 to 600 Celsius from the gas turbine, are directed to the heat recovery steam generator, HRSG. And HRSG will convert the heat into the high pressure steam. Why? Because the high pressure steam will drive the steam turbine and generates additional electricity and supplies industrial steam for the PIC. And the steam will exiting the turbine and condense back to the water in the condenser. Why? Because the water will recycle to HRSG for the next cycle. And last, it will be combined outputs, which is the electricity will deliver to the PIC and national grid. Meanwhile, the industrial steam for refinery and petrochemical operations. So there are many differences between conventional thermal power plant and cogeneration plant. So the first one is CHP, or cogeneration plant, recovers waste heat, which is it generates electricity plus steam. Meanwhile, the conventional thermal power plant generates only electricity. And cogeneration plant also provides a high efficiency compared to conventional thermal power plant. CHP also can reduce CO2 emission, which is carbon dioxide, compared to conventional thermal power plant. So we get the advantages of CHP, which is cogeneration power plant recovers waste heat, which is higher energy efficiency. And CHP also produces steam for industrial use in addition to electricity. CHP also can reduce fuel consumption, which is lower carbon dioxide emissions. And lastly, CHP can support industrial operation, which is it can give many operational benefits and economy. So guys, in thermal power plant, there are many calculations that we can observe, which is the first one is net power output and auxiliary power analysis. The net power output of the Pengerang Cogeneration Power Plant represent the actual electrical power available for external distribution and internal use after deducting the power consumed by the plant's own systems. So guys, as you can see, the power output details for this thermal power plant. The first one is the gross power output is 1220 megawatt, and for the auxiliary power consumption we get 5 to 10% of gross output. So the auxiliary power use is 60 megawatt, and the last calculation we get the net power output is 1160 megawatt.
So I'm going to be presenting about the type and amount of fuel. So for the type of fuel, the fuel used is natural gas, and it is supplied from regasification terminal at PIC. As to why natural gas is used is because it is cleaner than coal and oil. It also lowers CO2 emissions, and it can be supplied continuously and reliably. So for the amount of fuel calculated and the data gained from various AI sources such as ChatGPT, Gemini to do our statistics for us. So the assumption is that the planned electrical output is 1,200 megawatts. So the typical cogeneration efficiency is 55 to 60%, and the lower heating value of natural gas obtained is 50 megajoules per kg. So the estimated fuel energy input is 2,000 megawatts thermal, and the outcome is to produce 1,200 megawatts of electricity. The plant requires about 2,000 megawatts of fuel energy. So, for power consumed by pumps, fans, and other auxiliary equipment, so let me get to the details. What is auxiliary power? It is electricity used by plant's own equipment to keep the system running. Other than that, the main equipment for the auxiliary power is boiler, feed water pumps, cooling water pumps, condenser pumps, and fuel gas compressors. So, for the typical range for large cogeneration plant is 2% to 5% of total power output. So the chosen value for analysis is 4%, which is realistic and conservative. So for example of calculation for this part is gross electrical output equals to 1,220 megawatts, and auxiliary power fraction, which is 4%, 4% equals to 0.04. So auxiliary power equals to 0.04, which is auxiliary power fraction times of gross electrical power output, which is 1,220 megawatts. So the auxiliary power obtained by the calculation is 48.8 megawatts.
My name is Nazmi of VBS Reza. So we are going to continue with the stack gas losses. Stack gas losses are the heat released to the atmosphere through the exhaust gas after the heat recovery. In a combined cycle cogeneration plant, most exhaust heat is recovered by the HRSG, which means the exhaust heat is recovered by the heat recovery steam generator, leaving only a small portion lost through the stack. The assumption that we got from the industry practice, where the plant type is the CCGT plus the HRSG, which means the combined cycle gas turbine is flushed by the heat recovery steam generator. For the fuel, is natural gas and stacked gas loss fraction only 10%. The example calculation that we get is quantity of stack equal to quantity of fuel multiplied by the fraction of stack. The calculation that we get is quantity of stack is 1,000 multiplied by the 0.1, where 0.1 is stacked gas loss fraction, and the answer is 100 megawatt for the quantity of stack. So continue with the typical energy distribution. Electricity and useful steam only 60 until 70%. Stacked gas losses is negative 10%, and other losses is 20 until 30%.
So now I'm gonna tell you about temperatures at several locations of Pengerang cogeneration plant. There are 4 locations: intake temperature, gas turbine inlet temperature, gas turbine exhaust temperature, and condenser temperature. For intake temperature, the temperatures is 28 degrees Celsius to 35 degrees Celsius, which we follow Malaysia's climate. Air intake temperature is the air entering gas turbine compressor. Lower temperature shows higher density, and cooler air shows less compressor work. Move on to gas turbine inlet temperature. The temperatures is 1100 degrees to 1400 degrees Celsius. Gas turbine inlet temperature is the temperature of combustion gas entering gas turbine. Here shows that higher TIT, temperature inlet turbine inlet temperature, higher turbine power, and also it improves cogeneration efficiency. So hotter combustion equals to more electricity. The third one is gas turbine exhaust temperature, which is 567 degrees to 608 degrees Celsius. Here shows that gas turbine exhaust temperature is the gas leaving turbine and entering HRSG, heat recovery steam generation. Higher exhaust temperature, more heat recovered, and also better overall plant efficiency. And last one is condenser temperature, which is 33 degrees to 35 degrees Celsius. condenser temperature is the steam turbine exhaust, which go back to the condenser. There are two, which improves overall cogeneration efficiency, and it is the main place where waste heat is released.
Next is rate of heat rejection at the condenser. The condenser removes excess heat from the steam after it leaves the turbine before being returned to the boiler or HRSG. In combined cycle cogeneration plants, like the Pengerang cogeneration plant, this process improves turbine efficiency by maintaining the low exhaust pressure. For the assumption, the plant type is combined cycle cogeneration, the CCGT, the fuel is natural gas. The typical condenser heat rejection is 25% until 30% of fuel energy. The same value that we get is 30%. For the example calculation, the quantity of condenser equal to fraction of condenser and multiply by the quantity of fuel. So the calculation is 0.30, where the 30% multiplied by the 1000. So the answer is 300 megawatt.
All right, so for the rate of entropy generation measures energy losses and irreversibilities in the Planck equations, which is in the second law of thermodynamics. So for the rate of entropy generation, Sgen equals S out minus S in. So for S out, the formula is S conditional plus S stack. So for the entropy transfer, S equals to Q over T, with the Q being the rate of heat transfer over temperature. So for the thermal data used is gross electrical power equals to 1220 megawatts. So for auxiliary consumption is 4%. The net power output is 1171 megawatts. So for the net electrical efficiency is 55%. For the fuel heat input is equals to 2129 megawatts. So for the ambient temperature we have 298 Kelvin. For the combustion heat input we have 1600 Kelvin. And for the condenser heat rejection is equals to 310 Kelvin. So for the exhaust or stack losses is equal to 450 Kelvin. So the total rate of entropy generation that we calculated is 2.06 megawatts per K. So for the plant follows the plant follows thermodynamic laws. Irreversibilities mainly come from combustion process, exhaust heat loss, and large temperature differences during heat transfer.
So now we move on to the effect on environment. There are positive effect and negative effect. Under positive effect, there are three: reduced carbon emission, high energy efficiency, and waste heat recovery. For negative effect, there are continued rely on gas, water and thermal pollution risks, air quality impacts, and the last one is climate change and extreme weather.
So we have reached the end of our presentation, which means the conclusion. In conclusion, the Pengerang Cogeneration Power Plant plays a vital role in supporting the cooperation of the Pengerang Integrated Complex and Malaysia's national power system. By using cogeneration technology, the plant efficiency produces both electricity and steam, resulting in higher efficiency, reduced fuel consumption, and lower environmental impact compared to conventional power plants. In strategic location, large generation capacity and also reliable energy supply contributes significantly to industrial growth, energy security, and also sustainable development in Johor and Malaysia as a whole company. That's all from us. Thank you.